control, we have 240 volt DC shunt motor, armature resistance is given, and the field resistance is given as well, and the armature current at rated value is given as 40 amps. And the speed is 1100 RPM. So this is now representing the operation at full load, 40 amps and 1100 RPM speed. Find the developed torque. So simply, we have the value of current, we have the value of speed. So this means we have the data of one operating point. So simply, we can calculate the value of flux constant or motor constant, and based on that, we can calculate the torque. This is a method. Another method is to calculate the power and use the speed in order to obtain the torque, and both are equivalent. So here in this part of the problem, we said that EA, which is the back EMF, equals VA minus IARA. We obtain the value of EMF, and using the relation between EMF and speed, we can obtain the value of K phi, or as we said, we can calculate the power as B developed equals EA multiplied by IA. This is now the developed power of the motor, and we can divide this power over the motor speed in radian per second in order to obtain the value of the developed torque. So this is the first part. Second part, which was something was not correct in the question itself, the field rheostat is adjusted so that the field resistance is 150 ohms. So now we will change the value of field resistance. This means that the current, the field current will be changed. So this is now is considered as field control. We are going to control the motor field. Type. Find the new operating speed if the armature current remains constant. Here in this part previously it was written if the armature current and torque remains constant. It's not the right expression, because when we control the field current, if we go to now the Ward-Leonard method here, we have two parts of control. We have either voltage control or field control for Ward-Leonard method. So if you are going to control the field, this means the current and power will be constant. So current here will be constant, okay, and the value of torque will be variable, because we are going to change the value of K phi. So if you multiply now K phi by current, will give you the value of torque. So we make field control and keeping current constant and power as well. So this is going to make torque variable, not constant. So this was not a right expression in the problem. For that, I repeated the solution of this problem again here. Okay, fine. So the armature current remains constant, and this is, by the way, this is the target in most of control periods. We need to make current constant, so we have constant current control for DC motor, and we will discuss it inshallah today. Type what will be the operating speed, okay, according to the new operating point. We have constant current, we have field control. So based on that, if the current is constant and we are going to control only the field, so this means the voltage is constant. In this case, we can say now, if the voltage is constant, we can calculate the new value of IF. We have the value of voltage in the first case and in the second case. First case, the RF was 120. Second case, the RF is 150. So we can get the value of new field current. Now, for constant volt, because the volt will be constant for both of cases, because current is constant. So we can say now EMF is constant. So E1 equals E2 before and after. For that, we can say now Ka multiplied by IF1 omega 1 equals Ka multiplied by IF2 omega 2. This means that we can now omit Ka from the equation and compare the values in order to get the second motor speed. And for sure, the second motor speed has to be higher than the no load speed given before. Now the speed is 143.9, which means RPM as 1375. And if we compare this value to previous value here, we'll find the speed was 1100. So we are working now, Shabab, in this region. Okay, we are working now in this region. Right. Now, if we would like to calculate the torque, is it going to be constant, Shabab, or variable? Sorry, lower than the torque calculated before, or the torque at the lower than rated speed?
Should be lower.
Should be lower. Why? Because now we are going to, or we operated the motor at field weakening, which means we reduced the value of field, and therefore we expect to have higher speed and lower torque because the power is constant now. Simply, if we would like to calculate the torque here in this new operating point, we can simply say that the volume of the power will be the same because current and EMF are the same. So we can just multiply E by I for the second operating mode and just divide this value by the motor speed in order to get the new value of torque. For sure, the torque will be lower than the torque at the first operating point. Another example here for variable speed DC motor. So we have a variable speed drive system. Drive, Shabab, means the power electronics converter along with the machine. This is called the drive. So we have variable speed drive system. So this power electronic converter along with the motor are used to control the speed in order to be variable speed. Uses a separately excited DC motor. So we have separately excited DC motor that is supplied from a variable voltage source. The variable voltage source here means the power electronic converter. It's not the main source which supplying the power electronic. All of time, the source of the supply for the power electronic converter should be the same supply we have in our homes. For instance, AC, so the supply will be AC, okay, which is 220 volt. Yeah, Shabab. And the task of the power electronic converter is to achieve the certain operating voltage, the certain level of voltage, or whatever the value of V, if it is DC or AC, according to the motor, okay, V or frequency, if it is AC motor, in order to apply or control the motor speed. So here in case of DC motor, the supply voltage will be definitely AC of the drive, and the output of the power electronic converter should be suitable to the DC motor, which should be variable DC supply. So the torque and power profiles are shown in the figure below. So this is our control strategy. This is the torque and speed characteristic according to our control. So it's stated here that the drive speed is varied from 0 to 1500 RPM, which is the base speed, by varying the terminal voltage from 0 to 500. So in the first part, Shabab, we control the motor speed from 0 to 1500 RPM. So this is here the 1500 RPM. We control this the speed during this period or this region by controlling voltage. So we have now a mapping between 0 to 500 volt and 0 to 1500 RPM. Okay, so we control the voltage from 0 to 500 in order to control the speed from 0 to 1500 RPM. Right, with the field current maintained constant. So in the first part of the control here, by making voltage control, the field current will be constant. Yani all of the control techniques, Shabab, we do not control both of values together. If you are going to make voltage control, the field current has to be constant. And vice versa. For the field current control, the voltage has to be constant. So in the first part here, the field current is constant. This is expected. what is needed here يا شباب. Determine the motor's armature current. We need to calculate the armature current if the torque is held constant. So in the beginning, we need to have constant torque as stated and as clear here in the figure, okay, which is 300 Newton meters up to the base speed. So we need to calculate the current, شباب. Now we need to obtain the current at this region. What we have now, we have the voltage range, we have the speed range. طبعا we can start using any of the operating points. يعني this means that we can get the base speed here of 1500 RPM at 500 volt. So let's start calculating from that point. So we can say now at the base speed of 1500 RPM, VT equals 500 volt. And also we can say EA equals 500 volt. Why, شباب? Because this is considered as the no load speed. And even here in the problem, at the last part, it's stated here, neglect all losses. Neglecting all losses means we may neglect the value of RA in our calculations. So we can consider EMF equals to the terminal voltage. Right. So by neglecting the voltage drop across the resistance, so we can say now at the no load condition, the value of KFI can be equal to 500 volt, which is the EMF, over the speed multiplied by 2 pi over 6 to convert RPM to radian per second. So this is now the motor constant in voltage second per radian. Okay, so the units here is voltage second per right. And sorry, the pen is not working. Right. So this is now, شباب, the value of flux constant at the first region. Simply, we have the value of torque, so we can say now armature current equals torque over KFI and obtain the armature current. Right. Any questions, شباب? Is it clear? Good.
Yes.
Number B, the speed beyond the base speed is obtained by field weakening. Field weakening, this means we are going to now reduce the field current by controlling the rheostat, because here we have shunt motor, which means, sorry, this is separately excited motor. So we can control the field here in two different ways, شباب. If we used fixed supply, we can control the value of rheostat, or we can control the DC supply, which is supplying the field winding itself. So it can be controlled DC source. So the aim here is to make field weakening, which means we have to reduce the field current, while the armature voltage is held constant at 500 volt. So at the second region here, the task is to keep voltage constant and field current will be reduced. This is going to be made at constant current. Take care that in the beginning, also in the first region, the current was constant as well. Is it right, شباب? So in general, for V and IF control now, during the motor operation, we try to keep the motor current constant, or we call it as constant current control. Okay, this is very important, شباب, for DC motor. In DC motor, we operate the machine at constant current control at both VR or at field control. Right. So in the second part, we will keep the voltage constant at 500 and the current as well will be constant. What is needed here? Determine the torque available at speed of 3000 RPM if the armature current is held constant at the value obtained in part A. So at the same value of part A, we obtained already the current, which is 94 amps. At the same value of current, we need to calculate the machine torque. صح يا شباب? Determine the torque available at speed of 3000 RPM. So at speed of 3000 RPM, we need to calculate our torque. Simply, the field current will be changed. So we need to get the new value of motor constant, because we know that شباب, motor constant is Ka multiplied by flux, which is depending on the field current. So Ka phi now will be different value compared to the one we calculated in part A. How we can get it? We need operating point. It's stated that in the problem the speed was 3000 RPM at the given supply voltage and current, the same current here. So we have operating point. So you have current, you have voltage, and you have the operating speed. Again, it's stated we can neglect all losses, which means we can neglect the voltage drop across the resistance, so we can say easily Vt equals Ea. طبعا شباب, we can do that if Ra is not given in the problem, if the armature resistance is not given. However, if the armature resistance is given in the problem, we can easily get the value of exact EMF simply by saying Ea equals Vt minus IaRa. However, here, because it's not existing in the problem, we can neglect. This is very, very important. In our life, when you face any problem, don't consider the value that may be trivial, which may waste your time. You can assume the volt will be constant, because if you make it in for example يا شباب, the voltage drop and the resistance here may be 0.05 مثلا or 0.1 ohm. So what will be the value of the voltage drop? It will be very small compared to the rated voltage, so you can neglect. Okay, so you can make this assumption to take fast decision. This is very important in electrical engineering. Fast decisions may be needed in a lot of time, شباب. Okay, sometimes you need to take fast decision to avoid a very big problem, to avoid accident. So you have to consider the approximation in this case. Right. So here, شباب, we neglected the voltage drop across the resistance, and we can say now E equals V equals 500 volt. So we have E, and we have our speed. So we can say now E over K over omega, which is RPM multiplied by 2 bar over 60, in order to get the new value of motor flux constant. As you can see, the motor flux constant here is 1.59. It's almost one half. It's exactly one half of the previous value. This means that the current is reduced to half. The field current is reduced to half compared to previous case. So this is now our new value of K phi. We can now calculate the new value of torque by multiplying K phi by current. So the value of torque is 150 Newton meters. Also, we can say, based on the power calculation, we can say power over omega, and it will give you the same value as you can see. Is it clear, شباب? So here in this problem, similar to previous problem, here we used a V control in the first part, here at speed lower than rated or base speed, and we used field control at the field weakening part in order to make overspeed or increase our motor speed at the same constant power. Right. Now, how we can make this control? We said we can control voltage of field or armature. How we can do that in our life? طبعا يا شباب, conventionally we have many control techniques based on conventional drive systems. Like, for instance, in order to control the voltage of DC motor, we need a variable DC supply. Variable DC supply was obtained using DC generator. And this DC generator can produce variable DC as a function of the generator prime mover speed. So in order to control the generator speed, we need an induction motor. So we need another two machines in order to control the DC motor. This is called motor generator set. And it's still used in very old systems. However, طبعا يعني with the revolution of power electronics, the solutions of power electronics became very cheap compared to that يعني old techniques. So we use solid state converters. Solid state, which is nothing but the power electronic converters. طيب, what is the يعني where is the part of the block diagram we already discussed in our classes that we can insert our power electronic converter, or how we can use it to control our motor? We discussed in the previous lab the block diagram of our motor, and we discussed it also in the first class in the DC motor topics. So this is our block diagram of the motor. It's a function of electrical motor parameters and mechanical motor parameters, where B is the friction coefficient, Tm is the mechanical time constant, R is the motor armature resistance, and Te is the electrical time constant. So these are the motor electrical and mechanical parameters. This is load torque, this is supply voltage. So this is our motor model. We discussed also in our lab yesterday for the Monday session, and we will discuss it inshallah for the Tuesday session, how we can control our motor using PI control. So simply we have our motor, and in order to achieve a certain speed, we need a compensator, which is PID controller, and this controller will be control the motor by changing the armature voltage here. So this will be a function or based on a reference value of speed, and this is we are going to discuss it inshallah in details today in our lab for the Tuesday session. So where is the part of the power electronic converter here? This is now theoretical control. Where is the part of the power electronic converter? Actually, the PID controller يا شباب can be implemented in digital controller like Arduino, for instance. Arduino is considered as controller. It's not a source of power. So it cannot be generate the required voltage. So it just can generate some pulses with very few milliwatts, very few power, okay, which can be used to control another device, which is power electronic converter. So the power electronic converter exists here in this part. So it will take the pulses based on the digital controller, and the digital controller will implement the function of PID in order to deliver some pulses for a circuit. The aim of this circuit is to modulate the input supply voltage to be suitable to the output voltage needed for the motor. So the power electronic converter goes here in this part. Okay, and practically PID controller can be implemented within a digital controller, like Arduino, like any microcontroller, like FPGA, like microcomputer, Raspberry Pi, BeagleBone, whatever the digital controller can use. Okay. So this is here for voltage control. So we said that we need to make current control in all of the motor operation because it's very important to keep current constant. For that, there is another block diagram here representing the motor. This is our motor model, similar to that model. Okay, this is semi-linked model, by the way. So this general block diagram for the motor is supplied from a power electronic converter. As you can see here, this is a complete block diagram. It's not implemented on semi-link like these two blocks. Okay, or schematic diagrams. Here, this is considered as general block diagram. Okay, so here you will find the power electronic converter here. This is the power electronic converter, and the power electronic converter takes the control pulses from a controller. So all of these parts can be considered as controller يا شباب. All of these can be considered as a controller. Not this, sorry. All of these parts can be considered as the digital controller now. And this is now considered the motor. So this is our motor. This is the controller, and this is the power electronic converter. What is the aim here, or the purpose? The purpose is to control the motor with keeping current constant. For that, we have to sense the motor current by current transducers, current sensors, Hall effect, okay, any sensor for current, and there will be a feedback ratio for the current sensor for sure, okay, which can be controlled to a certain value of current. If we need a constant current, so the reference value of current will be entered to the digital controller, and after that the error of current will be mapped to obtain the volt. This is nothing but PID controller, by the way. The mapping here means this is PID controller, and the output of the PID controller will obtain the required voltage needed. And based on that, the required voltage needed will be translated as a controlling pulses for the power electronic converter. This is the concept now, Shabab. So we have motor, we have controller. The controller will provide some signals, some pulses for the power electronic converter in order to achieve a certain output voltage. طبعا يا شباب, the power electronic converter now has two inputs. One input as a supply and one input as a control pulses. So we have two inputs now. This is our supply, which can be the three-phase AC supply, for instance. It's according to the type of power electronic circuit you are going to use. And the other input here is the control signal, which is some pulses to turn on and off the valves or switches inside the circuit in order to achieve a certain voltage. Okay, so this is now how we can obtain a certain voltage for V control, and the same is also for IF control, because IF control needs a variable supply for the field circuits. So this is this technique or circuit or schematic can be used for separately excited, and those can be used for shunt motor, okay, by the same idea. So let's go in more details in the power electronic converter. This is one of the circuits used in power electronic converters for high power applications. And now we have different or better circuit compared to that one, okay, which is based on some new technologies in power electronic switches, okay, but we still have this type of power electronic circuits in our life. This circuit, Shabab, is called rectifier. A rectifier is nothing but converting AC supply to DC supply. How it works? Simply, as you know, if the supply is positive, which means the current is positive and V is positive here, if we turn it on, the switch S1 and switch S2, I said switch, it's electronic switch. However, this is called Thyristor, SCR, silicon controlled rectifier. The symbol SCR is abbreviation for silicon controlled rectifier, which is has a name of Thyristor. How we can turn on the Thyristor, we will understand now here, but let's understand firstly the idea of rectifier. So if we turn it S1 and S2, this is going to connect the positive supply here to the output, which is the motor. So this is now became positive and that became negative. This is, Shabab, in the positive half cycle. In the negative half cycle, the positive of the supply will be here. مظبوط يا شباب? This is for AC source. So in AC source, this will be representing the positive half cycle. So the positive will be in the upper part and negative will be down. And in the negative half cycle, the positive will be in the lower part and the negative will be upper. So the positive will be here. So we can now turn on S3 and S4. So if we turn S3 and S4, so the positive will come through S3 to the same terminal of the load, and the negative will be connected through S4 to the upper point here. The negative will be connected through S4 to the lower part here. So this means, يا شباب, now during a positive half cycle or negative half cycle of AC supply, we could convert the polarity to be all of time positive in the top and negative in the bottom here. So the motor will have DC supply now. So we could convert AC to DC by means of rectifier circuit. Right, how this rectifier circuit is working exactly, how this thyristor is working, let's discuss it here in the waveforms. Here we have a type of circuit, شباب, called the inductive load. Why it's inductive? Because we have RL in the circuit. So the AC source will see inductive load all of time, whatever the motor is DC or not. It's some coils, and the AC source will see that these coils are considered as a RL load. So for RL load, what is the concept of operation of the thyristor, شباب? Firstly, the thyristor operation, شباب, we have one condition to turn on and another condition to turn off. The condition to turn on is to have positive to negative volt across the anode to cathode when we apply the pulse. So we are going to apply a pulse here. At the instant of applying pulse, the voltage of anode to cathode has to be positive. So this means if the supply is positive in the positive half cycle, S1 will have positive here and will have negative here. So we can apply a pulse in the positive half cycle for S1. And you will find it's the same for S2, because S2, the negative of the supply will be in the cathode side, and the positive will be connected to anode from the other thyristor. So at the positive half cycle here, شباب, in the figure, from 0 to pi, we can apply a pulse. This pulse is called firing pulse. Firing pulse. So the thyristor can be fired. Fired means turned on. So the circuit is called the firing circuit, which is used to provide the pulse to S1. طبعا this circuit is not given here. So we have, in order to control any power electronic converter, شباب, we have two main circuits. One circuit is the power circuit. This is which is a drawn circuit here. Another circuit which is not drawn is a control circuit. In case of thyristor, it's called the firing circuit. In case of IGBT or MOSFET, it's called driving circuit. And these circuits, which are control circuits, are not drawn in the power circuit here. It's hidden because it's not going to be used to flow the main current here. Okay, the control circuits are just providing some few pulses with few milliwatts in order to control the operation of power electronic switches. Okay, so it's not important to include it here in the power circuit because there is no current flow will be in these control circuits. Right. So we have here, as we discussed, we can apply pulses for S1 and S2 at the positive half cycle. For that, شباب, when we apply pulse here at this angle, which is called alpha, the voltage is positive, and the output voltage, as you can see, this is the waveform of the output voltage, V out. It will be equal to the supply voltage from that instant, alpha. Right. Until what time? This is what we need to discuss now is the condition to turn off a thyristor. So we now discussed the condition to turn on. The condition to turn on again is to have positive anode to cathode volt and apply a pulse at this period. The condition to turn off thyristor or diode, by the way, okay, diode is uncontrolled element and thyristor is controlled element. The condition to turn off both of these elements, thyristor or diode, is to have zero current, or current falls to zero. So these devices will be turned off automatically if the current reaches zero. Type. In case of continuous current, the current will not be zero at all. It will be moving all of time, and it will be there for all of time. So what we can do is to apply a high voltage on the anode to cathode in negative polarity. This is called forced commutation. So the natural commutation is to have zero current. The forced commutation is to apply high reverse voltage on the thyristor or diode. Here, because the current will be continuous in the DC output, because this is the case for most of DC motors, so we have to apply the opposite or reverse voltage by applying pulses for the other thyristors. So if we apply pulses for the other thyristors here, S3 and S4, during the negative half cycle, it will object the switches S1 and S2 to high reversed voltage. And in this case, the switches or thyristors S1 and S2 can be turned off. When this can be happen, when the voltage be in the negative half cycle and we applied another pulse here after 180 degrees exactly. Why after 180 degrees? In order to have symmetrical AC component in the input of the supply. Okay, so we will apply here a pulse at pi plus alpha for thyristors S3 and S4, and in this case the voltage will be reversed again and starting from to be positive again like that. So as you can see, one part of the voltage here goes to negative, as you can see in this part from pi to pi plus alpha. This is why, Shabab, this is because the current is still moving, so the thyristor is not turned off. So we have a part of the voltage here in negative side. Like we said that we need DC source. Is the negative value of volt here is effective or will affect the motor performance or not? If is the negative value of volt here will affect the motor performance, يعني you know, for a motor, if we have our torque speed characteristics, this is omega and this is torque, you know, we said this is the motor characteristic or the operation of the motor like that. Omega will be positive if voltage is positive. Torque will be positive if current is positive. But now if the voltage became negative, what will happen to the speed? Shabab, what do you think?
It will reverse.
It will be reversed. Is it mean that at this part of the supply, because of the supply being negative in this portion, the motor speed will be reversed? Does it mean the motor will be reversing its motion during this small period?
No.
You are right. No. But why?
Because the average is positive.
The average is positive, but why we care about average? Why we do not care about the traveling period here? We have a part is negative. Why the motor will not be reversed?
The part is too small to be effective.
يعني small or large here in terms of what?
The time constant.
Time, exactly. So this is because of the time constant. The time constant for electrical supply is very small compared to the mechanical constant. So the negative part of the supply here is not effective because it's a very short period compared to the mechanical time constant. For that, the motor cannot be reversed. Even the motor will not feel this part. It will feel only the average part of the voltage. For that, Shabab, for the power electronic converter, supplying DC motors, we care about the average value. This is the average value. طبعا you know how to calculate any average value for a waveform. Just start integrating the waveform here from alpha to pi plus alpha. For the sinusoidal waveform, you will get this relation. Now, Vt, which is the output voltage here on the motor, or we can call it as V out now. Okay, but yani V out as instantaneous waveform is like that. This is V out, and Vt is considered as the average value of this waveform. So Pt equals what? Equals 2 multiplied by square root of 2 multiplied by Vb over pi cosine alpha. This is simply can be obtained by integrating the waveform from alpha to pi plus alpha. طبعا يعني average waveform or average value means integrating and divide by the period. Okay, so the relation of integration will be يعني I will not write it. It's not easy to write with mouse now. The relation from scratch is just 1 over the period, which is here considered as pi, because from alpha to pi plus alpha is considered as pi. So 1 over pi multiplied by the integration from alpha to pi plus alpha for the equation which is V maximum sine omega t. Or not V maximum, we can say square root of 2 Vb sine omega t. If you make this integration, we can get this final form of relationship. So this is now representing the output voltage of this circuit. So simply we can use this relation to calculate the required volt for our operation. So now for the figure here or for the waveform we can see here. Yeah, let's focus on the V out as a waveform here. For this V out, what will happen if we increase alpha?
The negative will be significant.
Which means the average value will be decreased. Is it right?
Yes.
You know the value of cosine, its maximum at 0 and equals 0 at alpha equals 90 degrees. Is it right? This is the waveform of cosine. Cosine is like that, شباب. صح? So at 0 angle, it's maximum, it's unity. And at 90 degrees, it's 0. And if you continue after 90 to 180, it will be in negative. صح شباب? Is it clear? So this is now the angle alpha, okay, versus time. So if we have alpha equals 0, this means we have the maximum value of voltage as a positive value. If we increase the value of alpha, the voltage will be decreased. However, take care, if alpha became greater than 90, the average value will be negative. The average value will be negative, which means the supply polarity will be reversed. What does it mean, ya shabab? If the supply polarity became reversed here?
The motor will reverse.
The direction.
The voltage will be reversed, not the motor. Not sorry, yani we cannot consider it's reverse motoring. We have to check first the current direction. So if the voltage is reversed and the current stay in the same direction, this can work now in regenerative braking. Is it right? Because the power will be negative. So this means the power will be returned to the supply. So it's not now a reverse motor operation. So we cannot decide now based on voltage only in this circuit. But later, inshallah, we will discuss some circuits that can be used to reverse the motor direction, okay, or to operate the DC motor in the 4 quadrants. Okay, shabab? As you can see here, shabab, the current is positive all of time, which means the current will be positive and the motor torque will be positive all of time. Okay, and this is considered as the AC current. So this is the current at the AC supply side. طبعا it's including here some harmonics, which means that rectifiers will inject harmonics to the electrical supply, which is not good. For that, we have advanced circuit instead of this circuit called PWM rectifier. PWM rectifier. But we are not going to discuss it here in in this level of course. Okay شباب. طيب. As you can see here in this part the voltage became negative, and the average voltage became negative here, and the current is in the same direction, which means now the power is reversed. So this is here at alpha equals 135, and this curve here is at alpha equals 45. So this is now representing, in this case, this is representing motor operation at that quadrant in positive, and the other direction here representing the operation at that quadrant. This is not reverse motor, however, it's called regenerative braking for the reverse motor. So the speed direction will be converted and the torque will not be converted. So this is considered as regenerative braking for the third quadrant, which is the fourth quadrant now. So this is represent quadrant number 1, and this is representing quadrant number 4. Okay, شباب. Is it clear, شباب?
Yes. Doctor, I have a question in the previous slide. Here, yes.
Yeah.
We said that the load is inductive, but
Yes.
does the thyristors affect the seen impedance from the source side?
Thyristor affect the impedance?
Yeah, we said the load is inductive.
Yes, the load will be seen as inductive, yes.
But the switches will affect the impedance or will not change?
Actually, it will affect the impedance. يعني the seen impedance here, the seen impedance value will be a function of the thyristor operating a firing angles. However, it's still during all of the operation, the supply here can see inductive load because the energy can be returned to the supply as we discussed. يعني all of time here يا شباب, this negative volt with positive current means power is negative, which means the power will be returned to the supply again. So we have here inductance, which is storing energy, okay, and return this energy again to the supply. So all of time, the supply will see the load as inductive because there is an interaction. It's storing and returning the power again to the supply. Okay.
Doctor.
تفضل.
Is all in the all types, and in the all time, if the power is negative, it's returned to the supply.
Yes, the meaning of negative power, it means the power flow is reversed. So instead of having power flow from electrical to mechanical, it means now from mechanical to electrical, which means the power will be returned to the supply.
And the value of the power will be the magnitude, but the sign it's for the from the source.
Yeah, the sign is the sign of power, meaning the direction of power flow.
Okay.
Okay. The time is due now يا شباب. يعني I wish that we could understand the operation of this circuit. Inshallah, next class we will continue discussing the different circuits used for DC motor speed control. Any questions شباب؟ طيب يعطيكم العافية، نشوفكم على خير إن شاء الله. السلام عليكم ورحمة الله.
عليكم السلام.